Hybrid programming, an effective teaching approach for signals and systems and DSP lab courses taught by Dr. Nasser Katarnavaz at the University of Texas at Dallas. This brief demonstration is about how hybrid programming provides a more effective approach for teaching signals and systems and DSP lab courses. The programming approach in most signals and systems and DSP lab courses is using textual code, such as M-file script or C. However, most students will learn this material more effectively if they can interact and experiment with their code in a more intuitive manner. To provide students with interactivity, analysis, and experimentation capabilities in these lab courses, a more effective teaching approach is needed. This can be achieved by using hybrid programming. Hybrid programming is combining textual code, such as M-file script or C, and graphical programming, such as LabVIEW. Math operations are more intuitive to perform in textual code, whereas building an overall system and interacting with it are more intuitive in LabVIEW. With hybrid programming, we get the best features of both types of programming. An interactive approach to signals and systems laboratory. The labs in this book include Introduction to LabVIEW, Introduction to MathScript, Linear Time Invariant Systems and Convolution, Fourier Series, Continuous Time Fourier Transform, Digital Signals and their Transforms, and Analysis of Analog and Digital Systems. In addition to the above concepts, applications are explored in each lab for students to understand how these concepts are placed into practical use. Digital Signal Processing System Design, LabVIEW-based hybrid programming. The labs in the book include getting familiar with LabVIEW, analog to digital signal conversion, digital filtering, fixed point versus floating point, adaptive filtering, frequency domain processing, DSP implementation platform using Texas Instrument architecture and software tools, LabVIEW DSP integration, and DSP system design. In addition to the above concepts, the book covers application systems using the hybrid programming approach. Real-time implementation on a DSP hardware target is also covered. The following example demonstrates an echo cancellation system using the hybrid programming approach. This LabVIEW block diagram depicts the algorithm implementation. The echo cancellation algorithm is performed in the MathScript node depicted by the large blue box. An echo is a reflection of sound that arrives at the listener sometime after the direct sound. Echoes are typically due to reflections off of walls or other hard objects. The echo signal can be expressed as the convolution of the original signal with two delta functions. An echo-free signal is attempted to be recovered from the echo signal by performing deconvolution with an echo cancellation filter that is based on the echo amplitude and echo delay inputs. The echo signal and what we hope to be an echo-free signal are displayed to the user and played through the computer's speakers when the corresponding play buttons are pressed. The autocorrelation of the echo-free signal is also displayed for a visual representation of how successful the echo cancellation was. The user interface seen here is the front panel for the code we just saw in the block diagram. The sliders for echo amplitude and echo delay adjust the numeric inputs to the echo cancellation algorithm. The effect that these values have can be seen on the graph of the echo-free signal. The autocorrelation of the echo-free signal is used to estimate the delay and the amplitude of the echo. The new estimated values for echo amplitude and delay can easily be adjusted to obtain very small autocorrelation side lobes. This will then provide a truly echo-free signal. Here is a video demonstration of how one can vary the parameters of the system interactively and do both quantitative and qualitative analysis in order to remove the echo from the original signal. First, let us set some arbitrary value for the echo amplitude and echo delay and run the program. Now let us play the original echo signal and the echo-free signal.
The discrete Fourier transform of a real-valued signal is conjugate symmetric. The discrete Fourier transform of a real-valued signal is conjugate symmetric.
As the delay is not set equal to the original echo delay, we hear the echo in the echo-free signal. Now let us change the value of the echo delay and run the program again. Note that we are looking for an autocorrelation having small side lobes. As you can see, the autocorrelation changes, however, it is still not optimum. Via experimentation, it is possible for us to identify the echo-free signal by seeing a sharp peak in the autocorrelation and by seeing the smallest side lobes.
The discrete Fourier transform of a real-valued signal is conjugate symmetric.
In conclusion, we see that signals and systems and DSP Lab courses can greatly benefit from hybrid programming. This holds true even when programming complex systems or performing system analysis. Hybrid programming provides a more effective teaching approach by combining the advantages of textual and graphical programming, providing interactivity and visualization capabilities, and driving shorter code development time. For more information about Dr. Katarnavaz's books, please visit www.ni.com/info and enter the info code UTDDSP.